In the previous video, we looked at solving for ML at large scale, but using various kinds of techniques that make use of the resources of a single machine. And that's fundamentally because the ML algorithm itself makes an assumption that the information exchange is possible using the shared memory construct. But what we also should know is that that kind of a model is typically restricted to a single machine execution because the latencies associated with accessing memory across the network is significantly higher, orders of magnitude higher than accessing the memory in the same machine. So therefore, for that purpose, it's important we understand how to truly solve for big data, ML at big data scale. So let's begin by understanding what is the constraint here that we need to work with. In fact, the constraint that we would work with is that there is no constraint. Not really no constraint. There is no assumption that we're making about resource availability. So specifically, this kind of a model is called as a shared nothing execution model. So the information exchange is having to go through at the minimum, basically there is no way to actually directly access the memory regions of another process. You have to go through an explicit step which exchanges the information from one process, rather uh, one process's outputs to another process's outputs. Right, the kind of like the shuffle step that we saw when we discussed about MapReduce. This is as contrasted with the shared memory execution model, where you directly access the memory regions of another process. So that way you get faster access to that data. You don't have to go through an explicit shuffle step, but you also have to deal with things like race conditions and that stuff like that. Like how do you prevent two processes from writing to the same memory region? Whereas in a shared nothing execution model, each process or processor or CPU core has its own memory region that's carved out for it, and there is no commonality to that memory region except for the fact that they all belong to the same RAM in that machine, right? That's about it. Otherwise, there's no common addressability. So in this kind of a model, which is called shared nothing execution, you can, if you build an algorithm that takes care of that's designed with this kind of a model, you could then run it on any CPU is running anywhere as long as it has its own memory allocated to it, which means you could run it on other machines, you could run it in a cluster of machines, etc. So massively parallel processing or shared nothing execution all mean the same thing in some ways. So they amount to the same thing. So if you design your ML in such a way that you leverage shared nothing execution, you can then scale it up to very, very large scale data processing. And that's how you truly cater to the big data need that you might have. So what kind of algorithms are conducive for the shared nothing execution and which ones are making assumptions about shared memory accessibility? So one of the first things that was analyzed right after the MapReduce paper got published by Google was the applicability of MapReduce for machine learning. So, in fact, there was this really interesting paper that came from Stanford, the researchers at Stanford, and later on, one of those researchers became super popular as a very popular figure in AI. His name is Andrew Ng, right? But at that time, Andrew Ng's lab, they were discussing whatever they were digging into which of the ML algorithms are conducive for expressing themselves using a MapReduce style computation. And they were trying to analyze what the common properties were, what the characteristics of such algorithms were. And they came up with a paper which summarized those learnings and then proved using simple pseudocode for some of the popular ML algorithms, how would they fit into this, characteristic? So the essence of what they found out or what they published at the time was most ML algorithms, which we commonly use today, but definitely that we commonly used even back then. That this is back in 2006. Most ML algorithms fit what is called as the statistical query model. So again, go back to what is ML trying to do, right? The ML is trying to actually exchange information about representations from the input data. And so what you're effectively doing is creating a model or force fitting a representation onto the input data. Uh, And the representation that you want to force fit or that you want to select as the winner is the one that maximizes the statistical likelihood that it explains all of that data, right? So that's what is referred to as the statistical query model. So specifically, in this kind of a model, the learning is based on summation of information over large samples. And the summation of information could be um, the information itself could be of various types, could be just the input data itself or some formula on top of the input data, etc., etc. So that summation over large samples is how the learning itself progresses, and you keep iterating on top of this various summations with some controls on what you do at the end of like summations over all the samples that you might have at your disposal. Then with that you have the construct that allows you to make progress and then eventually learn a representation. So that's what these algorithms are characterized as. So if that is the case, then the summation itself can be broken down using divide and conquer. And thus, you can achieve parallelism across a cluster of machines using a MapReduce style execution. So imagine if you think really about the summation as just literally a sum. We spoke about this in I think week 4 or week 3, one of the earlier weeks, basically. That if you just had a sum and you did sum over a cluster of machines using a shared netting execution model, you would break it down as a sum of partial sums. So the divide step would take the broader sum problem statement into calculating sums at each code level, if you think you can think of it that way. So for the partial sum that's computed by each core, you then take those partial sums and put it and bring it all to a single core, and in that single code, you take the partial sums and sum it up again, right? That's how we would do it. Likewise, if you think about what summation more broadly means, it's just basically a summation over a formula. But the formula is being computed over all the different data records, data columns of a record, right? So the summation is over all the records, and the values that you pick are basically columns in that record. So this means it's actually completely representable and executable using a MapReduce style, execution. More broadly, divide and conquer. So that allows the ML algorithm to then be parallelized using divide and conquer, using Spark, using MapReduce, etc. So this, summarization in the paper really opened the floodgates with respect to what does it mean for ML to operate at large scale. In fact, the paper went on to also, discuss about what is iteration, what characterizes these algorithms beyond just the summation. In fact, many algorithms are iterative in nature, meaning they iterate with progressively tighter thresholds, or they iterate on the output of that ML, output of that representation of fitment or degree of fitment of the representation, such that for each step, the error of the error by which the representation varies from the reality keeps reducing. So after a certain number of iterations, the threshold that is required for you to say that the representation closely matches the input data is met, right? And those kinds of setups, the iterations are unbounded, strictly speaking, but in practice, they end up becoming something that converges very quickly to a finite number of iterations, which are small in number typically. Right? It depends on the ML algorithm, obviously, but then and depends on the iterative capacity. Yeah, but most of these ML algorithms are iterative, and that allows, rather, that means that the problem of distributing that ML algorithm over a cluster in a shared nothing manner breaks down into iterations of summations, right? And then each iteration itself is controlled by a common thresholding function, and the thresholding function can be executed on a single machine, as an example. So then it becomes a series of divide and conquer steps, where a conquer is basically the conquer that happens at the end of each iteration. So, um, uh, so this entire setup is very conducive for then dealing with a bunch of different types of ML algorithms which are commonly understood. So regression, various types of classifications, like and even unsupervised methods like k-means, batch gradient descent, which is very common in deep learning, or even regular neural network learning. All of those now become expressible using either divide and conquer directly or iterations of divide and conquer. And that makes it really, really powerful, right? As a weapon of choice when dealing with machine learning at large scale. So that was what the paper had proved. And what heralded as a result was a bunch of different libraries that got produced where the algorithms were reinvented using MapReduce, using divide and conquer. So, like, think of scikit-learn that you see today. Back in the day, scikit-learn was, of course, not that popular. In fact, it might not even have existed in the current form. But nevertheless, there were well-known algorithms in academia, well-known implementations of those algorithms in places like Python, Java, C++. But because of this paper, because of the popularity of MapReduce at that time, um, uh, there were dedicated ML libraries that were produced, which took into account this particular way of breaking down the ML algorithm, right, using summations or iterations of summations. So, which algorithms are not conducive for this kind of parallelization? That's also important to understand. Anything that requires the ability to exchange information very, very rapidly, right? Because the moment you need to do that, you need to then um, basically look at every single record or a small set of records, or what's called a mini batch of records, which are used for training of specific part of the model in that CPU core. As soon as that training is done, it needs to exchange information with some of its neighbors or some of the other CPU cores. If that needs to happen, right, then the number of shuffles that end up happening is far higher than if you just shuffled once every, 1,000 rows, or once every 10,000 rows, or once every million rows, right? So basically the distinction is between if you were to do it in a batch versus if you were to do it in mini batch or even for every record, which is called as online, then the extent of information exchange that's required, the actual process of exchange, the shuffling that's required, is prohibitive in terms of cost. So let's explain why that's the case, right? In a typical MapReduce in implementation, you have maps executing in parallel. Once all the maps are done, then you go through a shuffle step. And once the shuffle is done, then you would have the reduce step. Let's assume that there are four cores in each machine. There are two machines, so eight cores in total. And let's assume there is one map per core. So if eight maps are running in parallel, you need all of those eight maps to finish. Only after all of those eight finish, you're able to then run the shuffle step. Because if you run the shuffle step before all eight finish, let's say seven finishes and one hasn't finished, but if you run the shuffle at that point, you'll have incomplete data being exchanged, right? Which is not right. So that type of a constraint where all the tasks in this particular step has to finish before the next task executes is called as barrier synchronization. So when you have bad barrier synchronization, it's actually very detrimental to parallelization performance, unless every single one of the subtasks in the step are able to finish at exactly the same time or nearly roughly the same time. So if you have eight tasks, you want eight tasks, all of them to finish at, let's say, 10 seconds each, as opposed to one finishing in 40 seconds and the rest finishing in 10 seconds, because you still have to wait for 40 seconds. So that skew in the performance could occur because of the unevenness. And then the shuffle happens, right? Now, if you had instead um, sorry, I'll just discuss one more thing. So each CPU core, when it executes a subtask, has latencies associated with spinning up the subtask for the first time, right? There's a context switch associated with it, reading the data that's necessary for that subtask to execute, doing its computations using L2 cache and RAM as well as the case may be, and then finally producing an answer back to the RAM, and then the RAM would be writing the data back to disk or not, etc. So there is actually finite overhead associated with executing that subtask in that particular CPU core. And that finite overhead is small when you do this subtask over a batch of data, right? Now, instead, if you use an algorithm which is online meaning every row of data that's processed needs some kind of an information exchanged with other cores, or if it's stochastic gradient descent, as an example, which is mini batch oriented, then for every 10 rows, every two rows, every three rows, etc., you're forced to exchange information between the CPU cores, which means you're forcing a barrier synchronization for every couple of rows or every row, which means the finite overhead associated with the subtask becomes that much more proportionately compared to the overall runtime of that particular task. So that adds up when you do the subtasks over millions and millions of rows, because that's what big data is really about. That's why it becomes prohibitively expensive, right? So for online ML algorithms, on the other hand, when you have a shared memory model, there is no barrier synchronization, right? So you don't have to shut down the subtask and force a synchronization to happen to exchange data. The data gets exchanged automatically because the memory is addressable. So these kinds of ML algorithms, which are online or which are mini batch oriented, are are best served using a shared memory execution model. But then you're limited in terms of scale, or you need to purchase a supercomputer which provides that shared memory abstraction for all of the CPU cores that exist across the entire computer. Okay, that basically is about ML being done at massive scale. Let's take an example and then dive deeper into this. So I'm going to take linear regression. That's by far the easiest to understand. So let's take a look at what is the summation that's involved here and how do we break it down in terms of divide and conquer. So what is the problem of linear regression? You're effectively saying that I've given a pair, rather a set of pairs of data points, and because we're talking about big data, these are millions in number, x comma y data points, and I need to be able to find a representation uh, of a formula, right, which linearly connects the uh, dependent variable y back to the independent variable x. Let's assume it's a single dimension linear regression. It actually doesn't matter. Like if it's multidimensional, it doesn't matter. So uh, this representation, I'm forcing it to be linear, and I'm basically expressing that representation as a linear equation which has variables associated with what the scaling factor is and what the constants are. And I want to estimate what should the values be for these two variables based on the input data that I'm getting. So the way to actually think about this is there is a weight matrix, which is M transpose, which gets multiplied by X, and then there is a small error constant which is added to it, which results in Y. So if I find what is an M that maximizes the extent of variation between what I'm computing as M transpose X compared to what I'm getting as the actual values of Y, that is the final answer that I need, right? So in other ways, rather in other words, I'm using least squares estimation. I'm trying to maximize what should be that extent of uh, match. Basically, minimize the error, the least squares error. So what is least squares itself comprised of? The best way to represent the matrix then is A inverse B, where A is basically this summation of the square of the input variable, which is the independent variables xi. Basically, you can just represent it as xi transpose, right? And you just sum it up over all of the elements. So, which is basically the square of the input vector. And b is basically the summation, which is a cosine, which is basically the cosine function of x and y together. So, if I do this product, right? Then I'll be able to get the estimated optimal value of this matrix, and that gives me the best representation empirically, right, that can actually fit this equation for that input data set. So, in a nutshell, I am effectively needing to solve for the summation of the squares of the independent variables, and then the summation of the cross dot product of the independent variable. So basically, I've boiled it down to a set of summations that I need to do. So using MapReduce, I can easily solve for this now, right? It's very well defined for me. So in the mapper step, first and foremost, it's millions of data points. So each data point is x comma y, and there's a batch of data points that's present in each uh, for each CPU core, right? So basically, each map task is dealing with a batch of data points. and that map task will basically sum up the local sums that's required. So, and these sums are completely computable just by looking at one record at a time, right? I don't need the sums to be, I don't need the products, the dot products here uh, to be across records. It's actually within the record, right? So it's easily doable as a map task. So each map task calculates the partial sums of both A and B, and then you shuffle these partial sums to a single machine. And at this point, the partial sums themselves are going to be uh, very small in number, right, in terms of total byte size that they occupy. So that shuffling of the partial sums to a single machine brings it all to a single machine, and there I can apply the reducer to compute the final sum, basically the final values of A and B, and then compute the final value of M, right? So that's my uh, uh, least squares estimator, which is minimizing the error. So in effect, I've solved for linear regression using MapReduce by looking at sums and then breaking down the sums across the machines. So with this, I'll just pause here. In the next video, we'll continue with the discussions on big data machine learning.